Hello, my name is Ethan Park, and I will be presenting my project on the comparison of scaffold designs of 3D printed scaffolds for bone regeneration tissue engineering. The purpose of this project was to find a solution for the disease osteoporosis. Osteoporosis is a disease that affects bone density, weakening the bone's overall structure and thus leaving a patient more prone to bone breakages. In a normal human, a bone breakage will result in the bone mass regenerating to a greater density than prior to the breakage, but in osteoporosis, that isn't the case. And when a bone breakage occurs, the bone will never be able to regenerate to its previous amount of bone mass, meaning that it's a degenerative process and creates a vicious cycle. According to the CDC, over 16.2% of adults over the age of 65 have osteoporosis. And you can see the effects of osteoporosis on the right, where you have the normal bone and osteoporotic bone shown at 40 times magnification. And you can see there's a clear difference in the amount of bone density. This project mainly focuses on tissue engineering as the source of this solution. What you have Tissue engineering is a emerging field in which you grow new organs from patients' DNA. This utilizes stem cells and uses a scaffold in aiding in this proliferation. If you look on the right, there's a diagram with an injured bone, and you would take stem cells from this injured bone, and using nanoparticles and growth factors, you would allow these stem cells to grow, and you would use a polymeric scaffold, and those cells will then grow into the scaffold and proliferate throughout the scaffold, and that scaffold with the stem cells would then be implanted in the bone, allowing it to fully heal. This project mainly focuses on these three articles as the source of its inspiration. These articles talk about the use of hydroxyapatite and polycaprolactone to create stronger scaffolds and different types of printing methods to create these scaffolds. However, I found that there's a lack of literature on the type of design of these scaffolds that should be used in order to create the best results for tissue engineering. And so the purpose of this project is to find the optimal design of a 3D printed scaffold to improve mechanical properties of a scaffold upon which bone cells may be introduced in tissue engineering. To find more about this, I used ABS, or acrylonitrile butadiene styrene, which is a commonly used plastic filament to mimic the qualities of a 3D printed scaffold. And this project would be used to serve as the basis from which other types of materials can be printed. So first I had to design the scaffold on a application called Fusion 360. I transferred and converted the file into a .stl file, which is a type of 3D modeling type of file. And this was then sliced using another application, and it was prepared as a .x3g file. This .x3g file is the type of file that a 3D printer can read, and by slicing the model into multiple different layers, the 3D printer will then follow those layers and the vectors to actually print it along the XZ axis and move up on the Y axis after a layer has been printed. I use three different types of models: the orthogonal, diagonal, orthogonal, and the triangular. However, the original triangular model had some modifications made to it to create the triangular V2 model. And after I had printed these, I used the Instron 3343 testing apparatus to test the 3-point bending properties of these scaffolds. The triangular V1 model was not used in this testing or like not considered, because it while it was being printed, the struts ended up merging together and creating a solid block of material, while I wanted a scaffold that had differentiated struts so that stem cells may proliferate freely throughout the entire scaffold. So in my results, you can see that the orthogonal model, here's the orthogonal model when viewed with Young's modulus and the density. Here's the diagonal orthogonal model, and this is the triangular model, and this is the triangular V1 model that was later discarded. You can see here that the triangular V2 has much higher Young's modulus to density ratio than the other two models. In conclusion, I had found some differences in the 3D printed scaffold dimensions. However, these were originally created in Fusion 360 to have equal measurements. So this warping was assumed to be due to the warping properties of ABS, and thus these models had comparable results. The Young's modulus was compared, and the triangular scaffold had a greater Young's modulus when compared to the other scaffolds, and exhibited a 16.2% improvement from current orthogonal scaffold models. The average orthogonal Young's modulus was 344.96 megapascals. The average diagonal orthogonal Young's modulus was 154.4 megapascals, and the average triangular V2 Young's modulus was 400.7 megapascals. And here are my references. Thank you for listening.